Uh, Thank you for inviting me to give a seminar, and it's great to be back in Dell, even if it's on Zoom, and it's also great to see many people that I haven't seen for years, and I hope you're all keeping well. Today I will talk about a topic that I worked on when I was a PhD student in Dal Oceanography, and it's also something I have been working on from time to time since then. So the work I'm presenting today involves a number of people. Chi was a visiting scientist. So he visited me for 1 year, funded by the China Scholarship Council, and Chi worked on wind work on mesoscale ocean eddies. And then Yang, he was a visiting PhD student. So he visited me a couple of times, funded by my Royal Society International Exchange Grant. And Yang worked on a longer time scale, so the decadal time scale impact of relative wind stress on the ocean. So Zhaioming was his PhD supervisor in China. So I also have been working with David Mundy in British Antarctic Survey on this topic. So if there's time, I will show a slide. I will work with Dave Mundy. Okay. So the motivation of this research actually is very simple. So the surface wind stress, which to a large extent drives the ocean circulation, can be calculated using this Bach formula. So tau here is surface wind stress, and rho A is air density, CD is drag coefficient. So CD can be a function of wind speed and also stability of atmosphere boundary layer. U10 here is 10 meter wind velocity, and UO is ocean surface velocity. So what this formula tells us is that the surface wind stress tau depends on the relative motion between the atmosphere and the surface ocean. So the larger the relative motion is, then the greater the surface wind stress is. But because over most of the oceans, the magnitude of ocean surface current speed is at least an order of magnitude smaller than the speed of 10-meter wind. So very often, UO, the ocean surface velocity, is neglected in the stress calculation. So the wind stress then is calculated based on 10-meter wind velocity alone. Okay, so if we could call equation 1 is the equation for relative wind stress, which depends on the relative motion between air and the surface ocean. And we could call equation 2 is a formula for, or the equation for absolute wind stress, in the sense that the wind stress now depends on the wind velocity alone. Okay. So as it turns out, actually, if we use equation 2, so basically if we use the absolute wind stress, we use this formula to calculate the wind stress, and it can lead to a positive bias in the estimate of wind power input to the ocean general circulation. So this bias or positive or this overestimate can be as large as 20 to 30%. So it's quite large. So if you think about the ocean is forced energetically 20 or 30% stronger, then it will have implications on the ocean circulation and also on the role of the ocean in our climate system. So this actually, as you can see, so this actually is my PhD work with Richard Goldbach, who was my PhD supervisor So that was quite some time ago. So I think Richard is in the audience today. I think I saw his name somewhere. Okay, so here's one explanation of what happened. So suppose we have a warm eddy in the northern hemisphere, so represented by this solid circle. Okay, so this eddy rotates clockwise. And this eddy is subject to a uniform zonal wind field, represented by this dash arrows, dash lines. So on the upper part, or on the northern part of this eddy, the ocean current moves in the same direction as the wind. And so the relative motion between wind and ocean current then is smaller than the wind itself. And because the wind stress depends on the relative motion between wind, or between the atmosphere and the surface ocean, then the stress on the northern side of the eddy is smaller. Okay, but on the northern side of the eddy, it's where the wind does positive work on the eddy, because that's where the wind and ocean current moves in the same direction. So taking into account the relative motion, the wind now does less positive work on the eddy. And on the southern side of this eddy, the wind blows against the surface current, eddy current. So the relative motion is greater, and so is the surface wind stress. And on the southern side of the eddy, it's where the wind blows against the current. So that's where the wind does negative work. And now taking into account the relative motion, the wind does more negative work. So now if we integrate over the extent of the eddy, then you will find the net power input or net work done by the wind on the eddy will be negative, which means the wind is a uniform wind field mechanically damp the eddy. Okay. So if this is true, if this schematic is true, then we expect the eddy energy to be reduced when relative wind stress is used in the calculation. Okay. So that's indeed true. So here is one example from a 1/10 degree idealized channel model of the Southern Ocean. Okay, so the figure shows the surface eddy kinetic energy in the model, in the surface of this model. So X and Y, they are the zonal and the meridional direction. So panel A shows the surface EKE when the model is forced by relative wind stress. And panel B shows the surface EKE when the model is forced by absolute wind stress. So absolute wind stress means the wind stress is calculated based on 10-meter wind alone. So what we can see visually, the eddy energy or eddy kinetic energy is reduced almost everywhere in this model when relative wind stress is used. So if we integrate over the whole domain, there is roughly about 20% reduction in the surface EKE in this model. Okay. And similar results were also found in a 1/12 degree model. It's a realistic model of the North Atlantic Ocean. So this is Carsten Eaton's work, and Carsten actually was also a postdoc in Dal, working with Richard. So from his work, so the panel on the left shows the eddy kinetic energy in his model when the model used absolute wind stress, and panel B here shows the eddy kinetic energy when the model is forced using relative wind stress, and panel C is a difference, so that's B minus A. So in his model, what he found is when the relative wind stress is used, there is about 50% reduction in eddy energy in the tropical Atlantic. So that's huge. So that's half of the eddy energy is gone in the low latitude, and the reduction is less. It's about 10% at high latitude. Okay. So we do have some model evidence that shows eddy energy is reduced or eddies are damped when relative wind stress is used. And here we're going to ask, we ask two questions. And the first question is there observational evidence of eddy damping by relative wind stress? Okay. And in this simple schematic we used earlier, the wind field is uniform in space. Right? It's uniform in space, which is not a bad assumption because the atmosphere wind tend to vary on a much larger scale than ocean eddies. But on the other hand, we also know that the wind stress, the large scale wind stress has a curve. In fact, the large scale wind stress curve is the force that drives the jar circulation. So this figure shows the long-term mean surface wind stress curve, and you recognize there are anticyclonic wind stress curve in the subtropical ocean and cyclonic wind stress curve in the subpolar ocean. Okay. So the question two we ask is, what's the impact of large-scale wind stress curve on wind work on mesoscale eddies? Okay, so maybe let's look at a simple example of an idealized Gaussian eddy, just to see what we expect from this. So the eddy, we're going to assume the eddy is Gaussian shaped. So eta here is the sea level anomaly associated with this eddy, and r is radius. So the sea level anomaly associated with this eddy is Gaussian shaped. It's described by this Gaussian function. A is amplitude, and LE is the size, is the radius of the eddy. So here we're going to assume the amplitude of the eddy is 22 centimeter, and the eddy is 100 kilometer. That's his radius. So those are just typical. Basically, it's a typical eddy. And this figure on the right shows the sea level anomaly associated with this warm eddy. That's the color shading. So in the center, eta is about 22 centimeter. And if we assume this eddy is in the northern hemisphere, then we can use geostrophy to derive the surface eddy geostrophic current, which are indicated by those white arrows. So this eddy is in the northern hemisphere, and it rotates clockwise, in a clockwise way. Okay. So that's our eddy. And now we're going to blow uniform wind over this eddy. And we're going to assume the 10-meter wind is in the zonal direction and has a magnitude of 7 meters per second. So again, it's just some typical value you can find in the real world. So that's the uniform wind. And then we calculate the wind power input or the wind work on this eddy. So using tau dot u, tau is wind stress, and dot us is here just means the eddy surface velocity. So naturally we will have this dipole pattern because on the northern side or upper side of this eddy, the wind is in the same direction as eddy current. So the wind work is positive. And in the southern half of this eddy, the wind blows against the eddy current. So the wind work will be negative. So it's very natural to have this dipole pattern. But one thing you notice is that there are more contours in the negative value region, so in the lower half than the upper half. It's just because in the calculation, we take into account the relative motion. And as a result, if we integrate over the extent of the eddy, then the total wind work will be negative. Okay, so that's for a uniform wind field. And now if we add a wind shear on top of this uniform zonal background wind field of 7 meters per second. Okay, so that's the wind shear with coefficient alpha. Alpha is, here we take the value, against very typical value. So we take the value of 1 centimeter per second over 1,000 meters. Okay, so now our wind field have a shear, or we could say the wind field have a curl now. Okay, so this is a negative curl. And now if we do the calculation again, so it's against tau dot u, well, again, we have this dipole pattern, but the difference now is that it's the positive value in the upper half of the panel actually is greater than the lower half. So if we integrate over the extent of the eddy, now the wind inject energy into the eddy. So the reason, of course, is because in this situation, the wind curls in the same direction as the eddy current. Okay, so what we can see is, for this simple eddy, if we have a uniform wind, and after taking into account relative motion, this uniform wind damps the eddy. But if the wind has curl in it, and if the curl is strong enough, it can potentially overcome the relative damping effect. Actually, it strengthens the eddy. Okay, so this is for a single value of alpha. So now let's vary alpha. So let's vary the strength of wind stress curve and do the calculation again for a variety, a whole range of alpha. And that's what we get. So what we have here is a plot of the average wind work, average over the eddy area, is plotted against the average wind stress curve in the eddy area. Okay, so there are a few lines. The blue lines are for cyclonic eddies, and the red lines for anticyclonic ocean eddies. The solid lines include relative wind stress damping effect, and the dashed lines has no relative wind stress damping effect. So basically, the calculation was done using absolute wind stress. So we notice a few things. First, as we expect, if the wind or the wind stress curls in the same direction as the eddy, it does positive work to the eddy. For example, when the wind stress curl over the eddy is positive, then it does positive work to cyclonic eddies and negative work on anticyclonic eddies. So that's opposite true for negative wind stress curl. And secondly, we find there is this linear relationship between wind work and the wind stress curl. Okay, and another thing we notice is that when we use relative wind stress, those straight lines they're shifted downward towards the negative side of wind work. Okay. All right, I'm sure.
Xaioming, I have a question here.
Yeah.
I see you here. So you don't consider Ekman here, right? So is any reason why Ekman can be just small enough to be ignored, or you have a specific reason for that?
I guess we are looking at the wind energy input to geostrophic current. So the wind also input energy to the Ekman current as well. So I guess we're looking at it separately. We're looking at the wind power input to the geostrophic eddy field, not to the Ekman field. But you are right. So there's also wind power input to the Ekman current. But I think throughout this talk, I will not talk about that. I mean, one reason for that, we don't focus on the wind energy input to the Ekman current is the motivation, I guess, is because the wind energy input to Ekman current, this energy tends to be dissipated in the upper ocean, and then the mixing associated with that energy dissipation will not contribute very much to the deep ocean or the ocean interior.
Well, that's partially right. If you have Western curl and can lift the isopignal, and you actually also can change your eddies, right? So then, it's that also can Western curl can contribute to the geostrophic part, right?
That's right. That okay. If I understand it's right. So the wind work. So when we use tau.u to calculate wind work, tau.ug, and so that's one way to understand wind energy input to the eddy or to the ocean. So I think there's also a paper on how you can calculate this using PW. So that's the wind energy input that actually below the Ekman layer. But so in terms of this relative wind damping, you can understand it through anomalous wind stress curve, and then the Ekman upwelling or downwelling associated with that. That's also, in some ways, that's a very insightful way to understand how it damps eddies. Although the calculation or what I show here is using tau.u, using this way to show damping, but this can also be understood as anomalous Ekman upwelling and downwelling inside the eddy induced by wind stress curve, anomalous wind stress curve. But they should be equivalent if you assume Ekman dynamics.
Yeah, it's idealized study, so you ignore certain things. I just want to maybe there's some estimation how much the impact on your. Okay, I think go ahead, please. Yeah.
Yeah. Okay. Good. That's a good question. That's a good question. Okay. So I'm just going to say something about this linear dependence between wind work and wind stress curve. So if that's the eddy we have, it's a very idealized eddy. It rotates clockwise with rotational speed US, and the eddy has radius R. And this eddy is subject to this wind stress. So the wind stress has a curve measured by this alpha. And if we integrate wind work, we'll find the net wind work is indeed proportional to alpha, so to the strength of wind stress curve. And for the same eddy, if it's subject to a uniform wind field, the relative wind stress damping can be scaled as this term. So this actually from the paper I had with Richard from my thesis. Okay, so this is relative wind stress damping. That's P2, and P1 is associated with wind stress curve. Then we can take a ratio between P1 and P2, and then plug in typical numbers. And what we find is that P2 and P1, they are comparable in magnitude. So that means both relative wind stress damping and the large scale wind stress curve, both potentially be important. Okay, now we're going to use data or data products to estimate wind work on mesoscale ocean eddies. The data we use are the satellite-derived sea level anomalies and sea anomalies. So, and then what Chu did is he identified the eddies from these weekly sea level anomaly maps using algorithm developed by Charlton et al., which is based on closed sea level anomaly contours. And using this method, Chu identified over 1 million eddies over this 10-year study period. And then from that, sea level anomaly, then we can estimate the surface eddy geostrophic current. So then we have US in the formula. For wind stress, we used quick scatterometer wind stress. And so what we did is, for each eddy we detected from sea level anomaly maps, then we co-locate the simultaneous scatterometer wind stress. And so for each eddy, then there's a wind stress at the same time, a same location, and then the power input to the eddy is calculated using tau.us. Okay, tau.us. And we also did another wind power input calculation, so the second one. And now we use the spatially filtered wind stress. So to spatially filter the wind stress, the purpose is to get rid of the small scale features in the wind stress field associated with ocean surface currents. And in doing that, then in the second wind power input calculation, we exclude the relative wind stress damping effect, because now in the second wind power calculation, the power input is calculated essentially using absolute wind stress. And then we can compare and contrast those two calculations to highlight damping by relative wind stress. Okay, so that's the wind stress field we use. So this is the original wind stress. So that's a scatterometer wind stress before we do the spatial filtering. And panel B shows the spatially filtered wind stress, where, as you can see, all the small scale features have all been removed. Okay, so this is the result. It shows the time mean here, because it means 10-year mean wind work on mesoscale ocean eddies. That's used the original scatterometer wind stress. So what you can see here is the color is more or less blue everywhere. So that means the wind work on ocean eddies is almost everywhere negative. And that's consistent with relative wind stress damping. Okay, I forgot to say actually, scatterometer wind stress actually is what it measured is relative wind stress. So it does have relative wind stress damping in it. Okay, and furthermore, the significant damping of eddies occurs in the western boundary current region and also in the Southern Ocean. So that's because damping of eddies is proportional to the wind speed and also surface eddy kinetic energy. And those regions, those are not only ocean storm tracks, but also atmospheric storm tracks. So there's a region where the wind speed is high, the winds are strong, and it's also has a lot of energetic eddies, the western boundary current region. So the damping is particularly strong in those regions. And then we can integrate the damping globally and get a number out of it. So this is from original scatterometer wind stress, which includes relative wind stress damping. And this is from the filtered wind stress calculation. As you can see, that widespread blue is gone. So So the damping is gone. And if we integrate over the whole domain, the net value is not so different from 0. So this in some ways highlights its relative wind stress that damps eddies. Okay, because the way we estimate wind work on eddies is by identify eddies from altimetry data. So that means we know which eddies are cyclonic eddies, which are anticyclonic eddies. So then we can then estimate wind work on cyclonic eddies and anticyclonic eddies separately. So this again is using original scatterometer wind stress, and the upper panel shows wind work on cyclonic eddies, and the lower panel shows wind work on anticyclonic eddies. And those bold solid curves, contours, they are the 10-year mean zero wind stress curve. So that marks the boundary of subtropical jars, subpolar jars. And then what we can see is there are large scale positive and negative wind work, and they are separated by and large by the time mean zero wind stress curve. So for example, in the subtropical ocean, the wind does negative work on the cyclonic eddies, but positive work on anticyclonic eddies. In some ways, it's as one would expect, I guess. So now if we do the same calculation, but using filtered wind stress, and if we compare that with the calculation using original wind stress, what we find is the large scale patterns, they are very similar because the filtered wind stress still have this large scale wind stress curve in it. So what's different is if we use filtered wind stress, the blue is less blue, so it's less negative, and red become more pronounced. So again, that's just because when we use filtered wind stress to do the calculation, we get rid of the relative wind stress damping. So it's less negative and more positive. And earlier on, so we also talked about this linear dependence of wind work on wind stress curve for a simple Gaussian eddy. So now we also look at this. Now we also plot this for the real ocean. So again, the y-axis shows the mean wind work average over the eddy area, and x-axis is the mean wind stress curve average over the eddy area. And the left panel shows it's for the ocean northward of 5 degree north. So that's the north hemisphere, and this is for the southern hemisphere. And these two figures are generated using original wind stress, which include the relative wind stress damping. So a red curve here is for anticyclonic eddies, and blue curve for cyclonic eddies. And those color shading, they are standard deviation. So as you can see, there's a lot of variability. It is not as simple as the idealized Gaussian eddy situation. But by and large, we still more or less get this straight line. It's not really that straight, but it's similar. This linear relationship still hold largely still hold, and so that's the same for the southern hemisphere. Another thing we notice is that this pattern is not symmetric about origin. So what it means is where the blue curve and the red curve intersect, they intersect below the origin, below zero. Okay, that's due to relative wind stress damping, because so that's what we had from the previous slide. If we now do the same thing using filtered wind stress, where we get rid of relative wind stress damping. Now those two curves cross at origin. Okay, so what happens is the whole pattern is shifted upward because the relative wind stress damping has been removed in the filter wind stress calculation. So the last thing to mention here is, so if we plot the number of eddies detected in this work against the mean wind stress curve, we will find most eddies detected, or I would say most eddies detected in using that eddy identification scheme are in the regions of anticyclonic wind stress curve. So anticyclonic wind stress curve means negative in the north hemisphere and positive in the southern hemisphere. Okay, so a quick summary for the first part. The wind work on ocean eddies, they can have a direct impact on eddy energy, and then it potentially modulate the role eddies, the eddies play. So I will give you one example towards the end of the talk. Damping eddies by relative wind stress provides a way of removing eddy energy in the ocean. So I guess the eddies, as we know, the eddies, they are generated by instability processes in the ocean, whether it's barotropic instability or Berkeley instability. But one of the key open question now is how and where the eddies are dissipated in the ocean. So damping eddies by relative wind stress can potentially contribute towards that question. So if we do a backward envelope calculation, we find the eddy spin down time due to relative wind stress damping is about a few years. So relative wind stress damping eddies may not be the leading process to remove eddy energy from the ocean, but it definitely can contribute towards that. And we find wind work on eddies, so the work done on eddies by large-scale wind stress curve depends on the polarity of eddies. So then this may contribute to the lifetime difference between cyclonic and anticyclonic eddies found in altimetry data. Okay. Okay, so now I'm going to move to the second part of the talk. So I think it's probably fair to say most studies on the effect of relative wind stress so far have primarily focused on ocean energetics. For example, damping of eddy energy or damping of near inertial energy, which is another important topic. However, the previous studies tend to use, they are typically regional ocean model simulations that last only for a short period of time. For example, in David and Thompson, and also my own paper with Richard, we ran the model for 2 years, and then we look at eddy energy difference in the second year. And in Costin's work, it's a bit longer, but still not very long. So then there's a question, what's the longer term impact of relative wind stress on ocean circulation and on the global scale, for example, on decadal time scale? I guess you could also ask a question, because so far we consider relative wind stress that basically include ocean surface currents in turbulent momentum flux calculation. Then you could ask, I guess, what about including ocean surface currents in turbulent heat flux calculation? Is that important? And to answer those questions, we have to use a model. So the model we use to address those questions is the MIT Ocean General Circulation Model, and it's eddy permitting. So it has a horizontal resolution of 18 kilometers and 50 vertical levels. It's a coupled ocean sea ice model and forced by 6-hourly Japanese reanalysis product. So in some ways, this is a typical global ocean model. It would be even better. It would be better if the resolution is higher. But this model is what was available to us at that time, and it's also at a resolution that we can afford to run. So we conducted 3 experiments, and I will explain what those 3 experiments are on the next slide. All 3 experiments, they are initialized from the same climatology and then integrated for 34 years with no surface root tolerance. So that means we want to allow the model to evolve freely. Then the model output from the last 10 years are analyzed and compared. Okay, so the first experiment is control. It's experiment control. So in the control experiment, the wind stress or turbulent momentum flux, the turbulent sensible heat flux QS and turbulent latent heat flux QL, they are all calculated using relative wind. So which takes into account of ocean surface current in all 3 bulk formulas. So that's experimental control. And in the second experiment, we call it none, which actually just means in none of the bulk formulas, ocean surface current is accounted for. So the calculation is based on 10-meter wind alone for wind stress and also turbulent heat fluxes. And then we conducted a third experiment, which is called heat. It just means in heat experiment, ocean surface currents are taken into account only in the heat flux calculation, but not in the wind stress calculation. So the purpose of this actual experiment is to help explain the difference between those 2 experiments, between control and none. So then we can take the difference between the 3 experiments to look at the impact of including ocean surface currents in the bulk formulas. For example, the difference between control and none shows us the impact of including ocean surface currents in all 3 turbulent flux calculations. And the difference between control and heat tells us the impact of including ocean surface currents in the wind stress calculation alone. Okay. So let's start with the forcing field to see what it brings about when we include ocean surface current. And this figure shows the difference in the magnitude of 10-year mean surface wind stress. And this panel shows difference between control and none, so control minus none. It's almost blue everywhere, and this is very similar to the difference between control minus heat. So again, if you recall, the difference between control and heat tells us the impact of including ocean surface velocity in the wind stress calculation. So in some ways, not surprising. So the difference in wind stress between control and none is because we include ocean surface current in the wind stress calculation. So one thing to say is it's overwhelmingly blue. That's just means in general, the ocean surface current moves in the same direction as surface wind. So that's and globally, the wind stress is weakened by only 4% when we take into account this relative wind stress. So it's a very small difference in terms of the mean wind stress. And if we look at the wind stress curve, so that's the difference between control minus none. And what we can see here is there are large differences in wind stress curve in regions of ocean fronts and jets. And they tend to form this dipole pattern. For example, in the Gulf Stream region, it's negative to the north of the Gulf Stream, and then positive to the south of the Gulf Stream. And we can understand this from this simple schematic. So if we have ocean jet that is subject to this uniform wind field, and taking into account the relative motion means the wind stress will be reduced most significantly at the jet axis. So the wind stress will be smaller here at the jet axis, but large away from it. So that means it will lead to a negative wind stress curve to the northern side of the jet and a positive wind stress curve to the southern side of the jet. And in some ways, the wind stress curve should be in opposite direction to the curve of the current. So the curve of the current here is positive, and then the associated wind stress, enormous wind stress curve will be negative. So that's the wind stress field. Overall, the difference is small, relatively small. Now, if we look at the difference in the time mean surface heat flux, things become more intriguing and interesting. So if we start from panel A, which shows the time average surface heat flux in the control experiment, the pattern is similar in other experiments. So as in other models, the model ocean gains heat at low latitude and then loses heat primarily in the western boundary current regions and also in the subpolar North Atlantic. Okay. And panel B shows the difference in surface heat flux between control and none, so control minus none. So there are a few outstanding features. First, there are dipole patterns in the western boundary current region. Okay. And another, maybe even more pronounced feature is that we have a positive surface heat flux anomaly in the subpolar North Atlantic, because this is a region where the ocean, the model ocean, loses heat to the atmosphere. So a positive anomaly just means now in control, the model loses less heat. Okay, and if we now compare this anomaly or this difference between control and none, and compare it with panel C and D, which shows difference between control minus heat, that shows the impact of relative wind stress, and D, that's heat minus none, that's the impact of including ocean surface current in turbulent heat flux calculation. And what we find is that this difference in surface heat flux is not due to including ocean surface current in heat flux calculation, but actually it's the indirect effect of including ocean surface current in the wind stress calculation. Okay, because this model is ocean only, so also ocean CLS only, so the atmospheric field is prescribed for, so they're the same for all three experiments, for control, heat, and none. So this heat flux difference has to come from the ocean, has to come from the difference in SST. So if we, in control, we have less heat loss, then that means in control, we should have a colder SST field. And if we look at SST difference, and this is indeed the case, it's negative so the difference between control and non is negative. And that again is due to the difference between, is similar to the difference between control and heat. So and as the fact that the heat anomaly difference and ST difference are opposite side shows it's a difference in SST leads to difference in surface heat flux, not the other way around. And this SST difference has to be due to ocean circulation differences between those model experiments when they are driven by different types of wind stress, whether it's relative wind stress or absolute wind stress. Okay, and if we now have a look at the wind power input to the ocean, so which is a quantity that is often looked at when in relative wind stress studies. So this figure shows the tau.ug. So that's the wind stress. Sorry, that's the wind energy input to surface geotropic current in the control experiment. So this spatial pattern is very similar to previous studies. Basically, the wind energy input is primarily concentrated in the Southern Ocean. And if we integrate over the whole model domain, then the total energy input is about 0.73 terawatt. And the difference in wind power input between control and non, so that is primarily due to relative wind stress effect. We'll find the energy input is reduced by about 0.13 terawatt, so which represents a 25% reduction in wind power input. So that's roughly in the ballpark of previous studies. For example, in Hughes and Wilson, so this is an observational study. They estimate wind energy input using relative wind stress, and they find the energy input is about 0.79 terawatt, and so we have 0.73 terawatt. And in Carl Wunsch's paper, he estimated wind energy input to the ocean general circulation is about 0.88 terawatt, but he used absolute wind stress. So if you add those together, then in our model, the energy input is about 0.86 terawatt when we use absolute wind stress. So it just shows the model seems to be doing a reasonable job in reproducing the power input difference between relative wind stress and absolute wind stress. So if we move on to the surface eddy kinetic energy simulated in this model, so this is EKE in control. It's all blue. It's all red. It's all positive. Of course, it's a positive definite quantity, and the spatial pattern, I think it's something we expect for model at this resolution. It's concentrated along the western boundary continental region and also at a low latitude and in the Southern Ocean. So what we're interested in here is what's the difference between control and non. And the difference is quite big. So overall, the globally integrated EKE is reduced by about 27% when the relative wind stress is used. And this reduction is not confined at the surface. So this shows the vertical structure of EKE in the three experiments. Okay, so the black curve is control, which includes relative wind stress damping, and then the red and blue are from non and heat, and they don't include relative wind stress damping effect. So this damping in EKE is not confined at the surface, although the damping effect is largest at the surface. It's actually, the EKE is reduced throughout the water column with a decay scale of 600 to 1,000 meters. Okay, so that's for the eddy field. If we look at the large-scale ocean circulation, there's also a noticeable difference. So if we start from panel A, which shows the barotropic stream function, so that's the depth integrated transport simulated in control. So this just we have the familiar subtropical jar circulation, subpolar jar circulation. And if we look at the difference between control and none, we'll find where it's red in control, it's now blue, and where it's blue, now it's red. So this just means after we include ocean surface currents in the Bach formulas, the jar circulation, the horizontal jar circulation is weakened. It's weakened, and this weakening. So if we compare B and C, I'm not sure you are still with me. So it's, if we compare B and C, they're very similar. So that just means this difference is due to relative wind stress effect, not because we include ocean surface current in the turbulent heat flux calculation. Okay, so if we want to put a number on it, and we find about 10 to 15% reduction in the strength of horizontal jar circulation due to relative wind stress effect. And that actually, in some way, explains the dipole pattern we see earlier in SST. As you can see, there is this also sort of a dipole pattern in the barotropic stream function as well. So if we move to the wind to mean mixed layer depth, which another is a very key quantity because it's related to deep convection in the model, simulated in the model. There's also a noticeable difference. So if we start with, again, with what's simulated in control, the mixed layer depth is deep in the western boundary counter region and also in the subpolar North Atlantic, particularly in Labrador Sea region, those regions. And if we take a difference between control and none, we'll find the mixed layer depth is reduced actually considerably, by more than 200 meters in the subpolar North Atlantic when the ocean surface current are included in the Bach formula calculation. And this again is due to relative wind stress effect, not due to not because we include U, also ocean surface current in heat flux calculation. And we think that's because this reduced wind stress curve in the subpolar North Atlantic, it weakens this preconditional effect. But in the subpolar oceans, there is cyclonic wind stress curve which leads to Ekman upwelling and then the asymptotic dooming towards the surface, which then eventually trigger deep convection. But the reduced wind stress curve in the relative wind experiment weakens this preconditional effect. But that's more research still need to be done on this to be sure this is the reason. So if there is quite a large difference in mixed layer depth or in the strength of deep convection in the model.
Yeah, sure, man. Just reminding, this is like already 1 hour, so just want to make sure other people have classes. Yeah.
Oh, sorry, I'm going to finish now. Okay, sorry. Yeah.
Yeah.
Okay, actually, the AMOC actually also has been reduced when the relative wind is included. So the reduction actually is about 13%. So it's quite large. So if both the horizontal jar circulation and the AMOC has been weakened, then if we look at the time mean meridional heat transport in the model, simulated in the model, we'll find the meridional heat transport in the North Atlantic. If we start with this one, there's a reduction of about 15%. And this, we think it explains why we have this cooling in the subpolar North Atlantic in this model. and the similar reduction is also seen in other ocean basins, and so the total global meridional heat transport is reduced by 0.2 petawatt. Okay, so that's the summary. This, I think maybe I will stop here. I'll stop here. I just want to say, maybe just say one thing. So it's not completely surprising. So what we find is including ocean surface current in air-sea flux calculations weakens the strength of global ocean circulation in a number of ways. In some ways, it's not completely surprising. If the wind energy input to ocean is reduced by 20-30%, then the ocean circulation will slow down in all kinds of ways, and it will have implications for ocean heat transport. Sorry, I ran over time. Yeah, I'll stop here then.
Thanks a lot. I know some people will have class and whatnot, but I think maybe some people might also have questions. So if you do have a question, feel free to stick around. Otherwise, don't feel obliged to stay past time. Does anyone have any questions out there? Jinyu.
Very good, Xaioming. I'm really glad, and clearly very convincing that relative wind effect is important, right? So no doubt for the circulation and the heat flux. But the bulk formula people use, to calculate wind stress from wind speed, the drag coefficient, right? CD, is dependent on wind, right? Yeah. That's the you either larger pond or modify. Do you have any thought how about surface wave could modify the drag coefficient, and how is that effect? I'm talking about relative importance of what you study here to the effect of the wave to surface wave. I'm talking about surface wave to the drag coefficient and other additional forcing to the moment equation and the mixing due to the surface wave. I'm talking relative importance. Do you know what I mean? Yeah. Okay.
Yeah, I think that's a very good question. I mean, we actually haven't talked about the wave effect at all. So of course the wind drives the ocean through the wave field, but here it's all swept under this CD coefficient. But ideally, I think I agree, we should use a wave model, a couple of wave model, and look at the relative. I guess if you have a wave model, there's still relative motion between the wind and the wave motion, and a relative motion between wave and the current, or wave breaking and the current. So I think that's probably still something that one can look into, but we haven't done anything on that. But this is very important to consider wave effect, and also the relative motion maybe between wave and wind.
Or maybe eventually we should have a couple system. Including the atmospheric circulation, ocean circulation, wave model, and the sea ice, and eventually everything can be included. That's maybe in the future, right?
Yes. I think when we look at the model results, in some ways not surprising, but in some ways it's also surprising, because all the difference between the model experiment is whether you include ocean current in the wind stress calculation, and then it leads to such a difference in terms of strength of ocean circulation on large scale and a meso scale, and also its heat transport. But yeah, so, and also we only have ocean only model, and it will be interesting to see if we have a couple in the model, and what's the impact it's going to have, because in the ocean only model we see there is a reduction in ocean heat loss to the atmosphere at subpolar North Atlantic, and how that is going to affect things like storm track, and how things are going to feed back to each other. So it's a very interesting question to look into.
Thank you.
Go ahead.
Okay, Yo doesn't mind if I go.
Yes, go ahead, Richard.
Okay, nice talk, Xiaoming.
Thanks, Richard.
But one thing that came to my mind, though, was that nowadays people argue that this relative wind stress effect should be modified, because in actual fact, the atmosphere also has some imprint in it from the ocean currents. There's some papers by Renault et al. From Jim McWilliams' group a few years ago. And so that can also have some impact. So instead of being, for example, U wind minus the 10-meter wind minus the ocean surface current, you'd only subtract something like 0.7 or 0.8 of the ocean surface current. So
Yes,
I mean, that's another effect that, and exactly what that coefficient should be that would make that modification is probably highly spatially variable and not easy to. I mean, I'm giving the example of 0.23, but it could probably varies considerably more than that. Actually, could have a whole range of values. In fact.
Yes, I totally agree. So this is actually the second question I have at the bottom of this slide. So yes, you're absolutely right. So the surface current feedback on the wind. So the wind actually knows the current.
Okay, surface current feedback on wind. Yes, sorry. Yes.
Yeah. So we in the work we did, we didn't consider that at all. But this will be a correction on the Park formula. As you said, it's instead of taking away 100% ocean surface current, maybe there should be a percentage to be assigned to it. But I would say that's probably a secondary effect. The primary effect is to include ocean current, and then how much you include is to be looked at in more depth. Yeah.
There's definitely an effect that's present in very high resolution coupled models, and the UK Met Office have run some very high resolution coupled models, and you can really see this effect in their model output. One of the students in Kiel actually did some analysis of one of their models and demonstrated that.
Okay.
But as I say, this correction, how much of the ocean current you should remove from the wind varies considerably.
Yep.
It's not just a constant coefficient, not just a constant number.
Yeah.
Okay.
That's right. I agree. Yeah, there's definitely something to look into.
Okay.
Yeah.
Thank you, Xaioming.
Okay, you want to squeeze in one last question here?
Last question. I have two actually. Maybe I think Xaioming, I'm a bit more criticizing as aside. So you work on this for over a decade. So in the talk, you didn't show any of direct observational evidence. This actually it's significant from the theoretical, from idealized study, but there's no evidence support. This actually, if we don't have that, how bad we are. There's surface drifters data set. I would imagine if we don't have maybe all the prediction of surface drifter will have certain bias, but you see you don't show that, and indirectly I would think they may have impact on the model bias. And so we are our ocean model. We know where we have level C bias, we can have a tropical bias, and so you don't show there's a if you include that we can reduce these biases, solve our problem. So I think that's a message I didn't get. I kind of I follow Jing's question on the waves. So if these are important on the current, they also be important on waves, right? Yeah. Why the wave community? There nobody I don't know. Maybe do they actually include the relative wind stress for their wave prediction? So there's I think a similar problem, right? So I think that's been my. So maybe my last question is you show the this damping on the eddies, so they're not on the surface, but also can penetrate on depth. You show your sensitivity study the difference. I guess my question is why is that? So we know the eddies are generated from the barotropic instability. They're not the surface, right? They have a depth. You have a surface damping, and why this information penetrates the depth? So that's last is my question. The pre one are my comments. Okay.
Right. Okay. There's a bit echo in your sound, so I'm not sure I fully get all the questions. So if I guess it correctly, so in the model we didn't show because the first question we didn't show the improvement on the model simulation, but we actually look at the difference. So because I guess we're more interested in to see the impact because I think the relative wind stress is there. So whether there's a coefficient you should put on when you take into account ocean surface current, but this relative if relative wind effect is to the leading order is there. So whether it's from the observational study or from modern study, it shows the effect is quite large. But whether if the model is biased, and then whether include the ocean surface current can improve that, it may not improve that because the model, I guess, could be wrong for all kinds of reasons, and there could be model bias for different issues. So actually, just to include this relative wind stress effect, it may improve the model, it may make it worse. But I guess what we are looking at is really to assess, how important this effect is. So for one slide I didn't get to show is this is a 1/12 degree realistic Southern Ocean NEMO model. So that's a model that Dave Mondi works on. So then Dave also look at the relative wind stress experiment and absolute wind stress experiment in the NEMO model. So this 1/12 degree model. So then he look at the meridional heat transport carried by the mean circulation by standing eddies, transient eddies, and I guess not surprisingly, in relative wind stress experiment, the eddies are damped, and the eddy polar world heat transport is also reduced. And as a consequence, if you compare the sea ice extent in the relative wind stress experiment and absolute wind stress experiment, there's more sea ice in relative wind stress experiment in this NEMO model. It's because the relative wind stress dampens the eddy, reduce the eddy polar world heat transport, which is then melt less sea ice. So I guess the study, whether this actually improves the sea ice concentration compared to observations, it does in some areas, but make it worse in other areas. So although we think we should use relative wind stress, but it's not guaranteed it's going to improve the model performance. Is that your first question? I'm guessing because I didn't hear it very well. Also, my